All right, question 6 says to compute the integral of the square root of 36 minus 9x squared minus 4y squared over the region R, where R is the set of all points x, y, such that 9x squared plus 4y squared is less than or equal to 36. And here we're going to make the substitution x equals 2u cos v and y equals 3u sine v. Okay, so this transformation feels really similar to polar coordinates, except you have this factor of 2 here and a factor of 3 here. Okay, so if you think back to the Calc 3 when you parameterize curves, okay, so let's say I don't have the 2 and the 3, so I just had u cos v and u sine v. Okay, well, if I think about u as being some fixed value and letting v vary, okay, I would just be describing a circle of radius u, okay? Now, if I uh, do stick in the 2 and the 3, okay, that's going to change the amplitude of x, so it would vary from 2u to minus 2u, and y, okay, now it would vary from 3u to minus 3u, and so in turn, you're going to get the equation of an ellipse, okay? So to fill that out in a little bit more detail, here's what I'm going to do. I'm going to take x and divide it by 2u, and I'm thinking ellipse here, so I'm going to go ahead and square, and then I'm going to add to this y divided by 3u quantity squared. And what is that going to give me? Well, x over 2u is cosine v, so I'm squaring, so I'll get cos squared v. And then y over 3u, well, that's sine v, so squaring will give me sine squared. And now I just have the Pythagorean identity, so that's equal to 1. Okay, so putting that a little more succinctly here, we're saying that if I think about u as being some fixed value, then this equation here will just describe an ellipse in the xy plane. Okay, so up here, I'm saying that if I fix u and let v vary, okay, then this relationship here will describe this ellipse here. And to make one trip around the ellipse, I can let v vary from 0 up to 2 pi. Okay, so now if I change u, what's going to happen? Well, I'm going to get a family of ellipses, right? So like, let's say I increase u a little bit here in this orange strip, okay? According to this equation, I'm just going to get this concentric ellipse out here, likewise for red, so on and so forth. Now, the one thing I cannot divide by 0, right? So if u is equal to 0, what can I say? Well, going back to these original equations, x and y would both be 0. So that's saying that all these points along the v-axis would just get mapped to the origin. Okay, so now what I'd like to do now is just with all of that in mind, let's go and look at this region of integration R here. What exactly is this describing? Well, here, if I rewrite a little bit, I'm going to go ahead and divide both sides by 36. I'm going to get x squared over 4 plus y squared over 9. This is less than or equal to 1, okay? And this right here is describing a region bounded by an ellipse, okay? And I can, to connect it to what I'm seeing over here, I could rewrite it as x over 2 squared plus y over 3 squared is less than or equal to 1, right? So when u is equal to 1, notice I just get this same denominator, 2 and 3 there, right, respectively. So in other words, this is going to give me the region bounded by the ellipse when u is 1, that's going to give me the boundary. So let me put that into the figure here. Okay, so I'm looking at this region in blue bounded by this ellipse, 9x squared plus 4y squared equals 36. Okay, and when u is 1, okay, if I set u equal to 1, I get this boundary ellipse. Okay, so in other words, in order to fill out this blue region here, R, right, our region of integration, over here in the UV plane, right, think about filling out this rectangle where I'm letting u vary from 0 to 1 and v is varying from 0 to 2 pi, filling it out with vertical strips. And each vertical strip, again, corresponds to one of these concentric ellipses, okay? So the benefit here is that now instead of integrating over this fairly complex region here in the xy plane, I can now trade that in and integrate over this region in the UV plane. And the bounds here are simply that u goes from 0 to 1 and v goes from 0 to 2 pi. Okay, so that's nice. Nice constant bounds there, just integrating over a rectangle. And what else do we need? Well, we need to address what's going to happen with the integrands. Let's go ahead and do that next. What is this going to equal? The square root of 36 minus 9x squared minus 4y squared with this relationship now between x and y and u and v. Well, if I look at 36 minus 9 times the square of x, that'd be 4u squared cos squared v, and then minus 4 times the square of y, and that'd be 9u squared sine squared v. And this is going to equal what? Well, notice this is 36u squared cos squared v, and this is also 36u squared now sine squared v. Okay, so I can go ahead and factor out a 36, and I'm going to be left with a 1 minus, and then here I'm going to get a u squared cos squared. So I'll go ahead and factor out the u squared from these two terms, and it's going to give me a u squared cos squared v. And then, right, factoring out that u squared, I'm going to get this sine squared v. And that's just 1. So in fact, I'm just going to get 36 times the quantity 1 minus u squared under the square root, okay, because here I'm just looking at what's inside the square root, okay, so that's not too bad. What's the other thing we need? Well, we need the Jacobian, right? We need to address what's going to happen with the area element dA here. So let's go ahead and look at that next. Okay, so here we're going to look at J of UV, and this is going to be the determinant of, and here I want to take the u derivative of x first. That's going to give you 2 cos v. Then take the v derivative, and that'd be minus 2u sine v. Then for the y derivatives here, I'm going to have the u derivative of y. That's going to be 3 sine v. And then for the v derivative of y, that's going to be 3u cos v. All right. And so taking this determinant, I'm going to get 6u cos squared v, and then I'm going to get a minus a minus, so that'd be a plus 6u sine squared v. And notice that will simplify just to 6u. So what does that imply? That says that dA, our area element here, is going to be, well, the absolute value of our Jacobian times du dv, and that in this case is going to equal 6u du dv, right? This feels like r dr d theta in polar, except we're getting this extra factor of 6, and notice that's just the product of 2 and 3. All right, so now let's go ahead and put everything together for the integral. Our integral now is going to be the integral from, we'll do 0 to 2 pi, and then integral from 0 to 1. So I'll do this in the order du dv. And then for our integrand, as we noted here, this is going to be the square root of 36 times 1 minus u squared. And then we have our differential area, right? This is going to be 6u du and then dv. Okay, cool. So now we're in pretty good shape because the bounds of integration are nice and constant. I can take this 36 out of the root, so that's going to give me a 6. And that'll multiply with this 6, so I get 36 there. And then I'm really just integrating u times the square root of 1 minus u squared. And notice also this integrand is totally independent of v, so I'm going to separate this out. So I'm looking at 36 times the integral from 0 to 2 pi of just dv. This is like the d theta integral, right? And then we're looking at the integral from 0 to 1, and this is u times the square root of 1 minus u squared. Okay, not bad. And now this is going to give us a 2 pi. And then here, we could make a substitution. Okay, I'm going to kind of just jump to the answer, but maybe, don't want to use u here because that's the variable here. But I mean, we could maybe say t is 1 minus u squared and go on from there. But yeah, what are you going to get? You're going to get minus a third times 1 minus u squared to the 3 halves, and then evaluate from 0 to 1. When you plug in 1, you'll get 0. When you plug in 0, you are going to get minus a third, but it's being subtracted. So this will give you a positive a third. So it's going to be 12 times 2 pi. That'd be 24 pi. Okay, so quite a bit more involved there, but really a good illustration of a lot of the main ideas. All right, thanks.